So let's now switch into what we were talking about last time as we dive deeper into regression analysis. And if all goes well, we should catch up from the snow. I believe we'll catch up from the snow. So we're going to finish off 15 and then move on to 16. I think it should be good. What did we talk about last time? Anyone? Positive and negative correlations. Tell me more about that. Tell me more, Rebecca.
Sorry,
Negative. Right, absolutely, right, because if one increases, the other decreases, etc. No, we're not claiming any causal relationship. Absolutely. We had a way of measuring correlation, the strength of that correlation. What was that measurement? Correlation coefficient. And what's the correlation coefficient? I can't remember your name, sorry. Marie. What's the correlation coefficient?
So it just basically like captures the strength of your direction of the correlation. So if the closer it is to negative 1 or 1, the stronger it is.
And obviously, if it's negative 1, it's negative. If it's negative, it's a negative correlation, positive correlation, right? Awesome. Now, one thing too we talked about is, well, we can identify these correlations, and we can even identify the strength of the correlation, but we don't necessarily know the cause. And more interestingly for us for today, we don't necessarily know, okay, if you increase 1, assuming we know the cause, if you increase 1, how much will the other variable increase or decrease?
And that leads us to
what? What did we talk about? The line of best fit. So recall we started with this. Y equals mx plus b. What does that represent? What does that in your high school days kind of represent? What was that? Okay. So it is a. Well, what does M in this? Slope. And what is B? The y-intercept. So we had a way to translate this into what we'll be working with. We might call it yi for the ith observation equals. Remember? The what? Yeah, y is the observed value, absolutely. And which is beta 0. So beta 0 is the same thing as b. Plus which we call beta 1. Multiply that by x1 bi. Recall? So we can set this up as, like age. We set this up last time as age and height. That. And I drew a line of best fit. Some of these are going to be right on that line. Some of them are pretty far away. Most of them sort of crowd near it. And that difference between what we predict on the green line and what we actually observe Oh, so this is x1i. Because as we will discuss, especially next class, we can have multiple x's. We can have multiple things that are explaining y. So what's this vertical relationship?
Residual.
The residual. Absolutely. So if we were to complete this, because technically what we have is we have an x value, and we put it in this equation, and we will get a predicted y value, but the actual observed y value isn't there, it's all the way up there. So this is how we complete it. Residual. But otherwise, it's very similar, right? It's just that this is just flipped around, and we add a residual term. If you're wondering, what is this? Does anyone know what that is? That Greek letter is? See a lot of scrunched up faces, which I think is, yeah, I really think, yeah. It is epsilon. Epsilon. Greek letters comes up a lot in this course. Epsilon. If you're wondering why it's epsilon, because obviously epsilon is the Greek letter for E, why is it not like the Greek letter for R? It's because sometimes the residual is called the error term. I don't like calling it the error term, though. I find it very annoying that some people call it the error term. When you hear error, what do you think? Mistake. Something's wrong, right? But nothing's wrong here. There's just some things we don't know. That doesn't mean it's wrong. It just means it's hard. So, a lot of people call it the error term. A lot of also people call it the residual. I find residual to be much more descriptive and reasonable, because it is, residual means what's left over. Right? The stuff we don't know. It's not a big deal, we don't know some stuff. Right? It would be nice if we knew it, but it doesn't invalidate the analysis because it's not a mistake necessarily. Now the goal of that green line is to minimize this value, the residual sum of squares. Right? What is this equal to? Mm-hmm.
And starting with one, but then that
Mm-hmm.
and then in parentheses the observed y separation.
Mm-hmm.
And that is squared.
Exactly. And in case you're curious, what's the difference between this equation and this equation? Is y hat I equals beta 0 plus beta 1 x1I, but there's no epsilon. There's no residual, because this is what we're trying to predict. So we're not going to include some like custom random value for every observation. This epsilon is really big, this epsilon is really small, that epsilon is kind of large, etc., etc. So we have all of these residuals, we square all of these values, thus if they're negative they become positive. Add up all these values together, and then that result, that RSS, that residual sum of squares, is as small as it could be. We cannot draw a line that would result in a smaller RSS. Don't ever worry about having to calculate this by hand, because no one in their right mind would ever try to find the line of best fit by running it through the numbers. For one, if you were to do it, you wouldn't like draw a random line and then guess and check as you get smaller. I mean, there is like an equation you would put it through, but it takes a while to do that equation, and computers are really good at that. Everyone does it through the computer, and I'll show you how to do it in Excel today. Super fast.
Any questions on this? Does it preclude you too of what we'll be working with?
Keep in mind that this equation, which is what we're going to, the whole point is we're going to estimate this line. Keep in mind the logic behind this line is exactly the same as this. Imagine we had an equation y equals, I don't know, 3x plus 8. If x equals 1, what does y equal? Well, actually, let's make x equal 2. If x equals 2, what does y equal? 14. How did you get that? Exactly. If x increases by 1, y increases by how much? 3, right? The slope. This then is logically equivalent to if I had to set it up this way, y equals, the hell I have there. Exactly the same thing. If you wanted to predict what someone's height is at the age of 2, obviously this doesn't apply here to this equation, but then you would get 14. And if you want to know how much y increases if you increase x, you look at the slope. And you don't care about the intercept at all. Logic is exactly the same thing. Okay, so what I want to do now, before I show you how to actually do this in Excel, I want to turn the clock back a little bit to a few weeks ago, just before the exam, when I had to do this group work. Do you remember this group work? How many of you completed the whole thing? Raise your hand. How many of you looked at the answers for the whole thing? Oh, awesome. Most of you.
So, you would then remember the last question, which is the one I want to talk about.
In the last question, we have Gideon, who is designing a new exercise routine. There it is. The leading routine results in an average of 7.9 pounds of weight loss per month based on the sample size of 10 people. That's all. Gideon doesn't have a lot of strength, so we had to rely on 10 people. With a sample standard deviation of 1.4, Gideon's routine average 8.6 pounds per week lost per month. I'm sorry, 8.6 pounds of weight loss per month. What's the highest level of statistical significance Gideon can claim? Don't limit yourself to 90, 95, 99, 99.9%. Any level between 0 and 100% is possible for this question. So, how would you answer this question? Do you remember? Since most of you looked at the answer key, you should remember how it goes. Well, so the first thing we do is we just do a typical t-stat, right? We have to do t because we're using a sample standard deviation. So t, we'll throw the absolute value in there, and then we have what is that? 1.4 in the denominator, square root of 10 in the numerator, and the denominator of the denominator, and then the numerator, we're looking at what, 8.6 minus 7.9? And if you do that math, you get 1.5811. Now, normally, if this was an ordinary question, you would look up the critical score with 9 degrees of freedom because we have 10 observations, so 10 minus 1 is 9. And then you would compare that critical score at these various levels, and then you would find statistical significance or not, and then move on with your life. But that's not what I asked. I asked, if you could pick any level of confidence, what is the highest level of confidence you can claim? Another way to put it is, what is the smallest alpha you can claim and still get statistical significance? Because of course we can just make these, 0.1 and 0.05 and 0.01 and 0.001. The other way, what is the smallest level, what is the smallest alpha you can claim and still get statistical significance? What I was asking you, in other words, was for the p-value. I'm mentioning this now because when Excel gives you the results of regression analysis, it gives you t-stats, calculated t-values, just like you've seen. It also will give you the p-value. And it's kind of more useful to look at the p-value than the t-stat because with the t-stat, you have to look up, critical value when you compare, p-value, still what you need. Just compare it with alpha, or whatever alpha you want. You don't have to look anything up because it's going to be built in. And to show you how it's built in, let's answer this question. So we essentially want to know if we go 1.5811 standard deviations over, what's that area? Noting this is a one-tailed test. What's that area? Does anyone know how we can do that? Anyone? Remember, we had this. T inverse. Not T inverse, because T inverse means we start with the shaded area and we pop out this. But here we know what this is. We know it's 1.5811, so we start with T distribution. 1.5811 with 9 degrees of freedom, making it cumulative. Now, if we do that, we will get this area right here, because it always takes that value to the left. So you'll want to take 1 minus that. And if you put that in, you will get 0.074. That would be our p-value. That is the smallest level of statistical, the smallest alpha we can claim, and still claim statistical significance.
What does that translate to on top of this level?
92.6. Slightly higher than 90%, but not quite 95. And indeed, if you were to look up the critical value for 95% at 9 degrees of freedom, you will get something that's larger than this. One of the things that gets a little confusing is that larger t values results in greater levels of statistical significance. But because the alpha is sort of the reverse of the t value, smaller p values result in greater levels of statistical significance. If this was 0.007 rather than 0.07, we would be able to claim it at 99% statistical significance, and more than that. 99.26. So to use it,
If P is less than alpha, it's statistically significant. So keep that in mind.
Because it's going to give you the p-values, and the p-values are super useful because the p-values embody this step right here. Right? They find the critical value for you. Is essentially that explanation. If you want to go in. Yeah, 1.833. If it was 95%. Again, one half test. Okay? Are we good? Awesome. Let's dive into it now. So if you want, please go to my website and pop into BS8210, pop into I'll pop into teaching, pop into BS8210, and we're going to download dataset 5. We're going to go dataset 5. And you will see that this data set might look a little familiar. You know what this data set is. What is this data set? Rate by professor data. Tell me more. What do you mean?
So that's like yes. Because you're not wrong. Oh, you're absolutely right, of course. So this is giving us those details.
Right. So I collected this data July 17th, 2014. So shortly after I had, so I was going to come here to Montgomery College. I think I started earlier that year. Yeah, I started in, what's it called? January. So during the summer, I got this data. And I wanted to update it, but since then, my professor has changed its presentation style, and so it's hard to get a bunch of data like this all at once that I can just immediately copy and paste to Excel, maybe rearrange it a little bit so that it looks nice. I would have to, if I were to do this again, I would have to import things individually by hand. I'm not doing that. So I'm just going to stick with this 2014 data. And this only focuses on people that had at least 25 ratings. So we still get a lot of observations. We have 211 individual professors just at Montgomery College. We have the department that they are in, which is pretty nice. We also have the total ratings that they have. And we also have a level of their quality, how people view their teaching, as well as their difficulty, how hard they are. Of course, lower values means it's easier, higher values means it's harder. And of course, we know if they're hot or not. That's also very important. So, what do you think is the relationship? The two ones we're going to focus on are D and E. What do you think is the relationship between these two? Between quality and difficulty? So you think they're negatively correlated? How strong do you think that correlation is? That's the correlation coefficient. Or you can just tell me what it is. Let's figure out what it is. What would be the correlation coefficient? How do we find that? How do we find anyone? Equals correlation. And so, we're of course just going to put this in, we're going to highlight. Do not include D2 or D1, because obviously D1, nothing is there, D2 at the time of what we're looking with. So we're going to go all the way down to D2, 13. Comma, and then go all the way back up from E3 to E213, giving us 211 observations. And when you enter, what do you find? Yep, negative 0.76. That's pretty high. That's a pretty strong correlation. That's quite strong. That's very strong. So that's interesting. But knowing correlation is not enough. We be kind of curious. What's the story there? What is going on? Why is it that it seems to be easier professors get higher ratings? Why is there that connection? So what was that, Anna?
People get better grades for being a professor. More likely
Ah, so you want to make a causal claim that difficulty causes quality. You're making a causal claim. That's important because in regression analysis, you always make a causal claim because you have to declare which one of these variables is the x and which one of these variables is the y. So I think that's a story a lot of people tell. I think it's a very familiar story. You know, if you make things easier, people will like you and they'll rate you more. If you make things hard, people don't like that. Is there another story we could tell? Is that the only story you could tell? Okay, but why? Yeah, maybe great professors just make things seem easy, right? I don't know for sure what is the right answer, but you can see how we can tell two very reasonable stories for each direction. I think they're both right, honestly. I'm not sure which is a stronger impact, but I think you can tell a great story for both of them. No, this is what we were doing when you do it for your memo, right? Essentially, you're saying, well, there's a probably connection between these two things. You don't need to do a correlation coefficient, but there's probably a connection between these two things. I'm going to tell a story as to why one would cause the other. That if a professor decides to make their class easier, they should get a higher quality rating, right? Or if the professor gets better at their job, then people think they're easier, right? If one thing changes, the other should change. That's the story that we're telling. You just have to pick one. Now, in your memo toward the end, I'm going to ask you to try to challenge your own argument a bit. Note there's a problem. Typically, you find a confounding variable, like maybe there's something that causes both of these things, like maybe it's the nature of the discipline that causes both of them, maybe. Which, by the way, we can test because we've broken them down by groups. So if we organize it by groups and then we just pull out only the English professor, only the math, I picked those two because we have a lot of observations. We can maybe control for that. But that would be a potential confounding variable. So what I wanted to ask you to do in your memo is come up with a confounding variable. Because there is give here. No analysis really is final. Every analysis that's performed is just part of a larger conversation. So we have this interesting conversation. Maybe difficulty causes quality, maybe quality causes difficulty. I'm going to focus on the first one because that's the one that is the story that's typically told. So what I want to do is I'm going to do this. I'm going to need to get access to the data analysis tool system that we have on Excel. Remember how we do that? How do we do that? Okay. File options. Add-ons. Go. Analysis toolpath. This was already checked from last class, but of course you don't have to check yourself. We hit it, and we have data analysis already. So everyone has data analysis. And when you pull it up and you scroll down, you should see something that begins with R. Random number? No. Regression. Also, yes. Regression. So here is where you declare which one is your dependent and which one is your independent. And make sure if you're having trouble making it work, you have to hit the enable editing. If it's not working, that's why. So once you hit the enable editing, essentially pull this up. So which one is our X? If we're gonna focus on the first one here, which one is our X? Difficulty. And which one is Y?
So I'm going to highlight the quality one first. I'm going to include D2 because I want to be able to press the analysis and press the label button. Then we're going to scroll all the way up and use faster. There we go. And then default is up. Now I hit the labels option.
So I have in Y, D2 to D213, and I have an X, E2 to E213.
There we go. Next, you have to tell it where you want it to print, because it's going to give you a lot of information. It's going to print a table of stuff. So, let's just put it somewhere nearby. Let's put it right here. I don't know. I3. Right there.
So I hit the output range, and then I selected into here and selected I3.
And this will, indicate the upper left-hand corner of the information it will print out.
There's a lot of other stuff here for other kinds of analyses. Like if you want to know the residuals for every single one of these 211 observations, you can select the residuals button, and it will print out an initial table with 211 observations and tell you the residual.
Which is not helpful for you right now, but it's pretty interesting. Questions? So, let's scan some of this and see how it works. Does everyone have something that looks like this?
You see we have 211 observations here. We have some stuff we'll talk about next week. Here's some more stuff we'll talk about next week. But note, here is RSS, residual sum of squares.
It's about 67.
Yeah.
What did you put on after data analysis? Data analysis, regression.
So you go down to the regression section right there, and then you click OK, and that will give you the table. And then you put in D2 to E13, and E2 to E13, hit the labels, place a good place for the output, etc., etc.
Okay. What we want to focus on is this section right here.
Our coefficients, our p-values, or if you want t-stat if you prefer. Note that the standard error, if you take the coefficient divided by the standard error, you get the t-stat. Fun fact. We also have this stuff right here. This is a confidence level. You can ignore it, but if you're ever curious to see, like, well, maybe the value is a little different than I think it is, this will give you the upper and lower bounds. But we want to focus on the coefficients and the p-values. What do you think this is right here? 6.2112. Give me a hint. The coefficients are our beta values.
Quality equals.
Anyone? What does this say right here? Intercept. So minus, because this is negative, 0.8625 roughly times D.
So that's just the line.
That's the line.
But then, what do you do with the
Nope, because the residual is for any particular observation. This is, what we are curious about is the line. We want to know what we would predict. So in other words, the coefficients are the beta values. Beta 0 is the intercept. Beta 1 is the difficulty, right? This is the difficulty right here. This is the beta 1. This is the beta 0. This is why it's important to put labels, because when we put multiple variables in, you'll have a table. Well, this might be like some other thing, like hotness, and this might be some total number of ratings and so forth. So you want to know which one of these corresponds to which variable. Any questions so far? So this gives us our line of best fit, which I can translate over here. And I can throw in, technically I can throw in this. Right? If you're like, oh, where is it? Oh, there. Right. We don't need an epsilon because we're just estimating. So immediately I know that if I were to make my class harder, I can expect by 1 point, I can expect my rate per professor rating to fall by 0.8625, assuming the causation works the way I think it does. So, what do you think the rest of this crap is for? Well, like I said, there's a strong connection between t-stat and p-value, so you really only need to look at one. Let's get some practice with p-value. What does p-value represent? Let me ask this. I use this based on 211 observations, 211 professor ratings. Imagine I did this exact same analysis, and you don't know the results of this 211 one. I did the exact same analysis, but I used only 12 professors, 12 ratings. And let's suppose, too, I got this same result, 6.211, da-da-da. Which analysis would you find more useful? The one with 12 or the one with 211? Exactly. Why, Adam? There's more information, right? We know more. The coefficient does not include anything about how many observations you have. It doesn't, by the way, use the things that we would care about to determine statistical significance. It's just trying to draw a line. But the p-value and the t-stat, these things do, right? This is the stuff we did last unit. So we check this to determine the line, but we check this to determine statistical significance. And I mean, they talk about the p-value for the intercept, no one cares about the p-value for the intercept. Right? We care about this one. So what is the p-value for difficulty? Exactly. So you see this, 1.9 E negative 0.1. That kind of reminds us that E is not for diversion. I'll be astonished how many times people see that E. It's like, I don't know what that is, so I'm just going to ignore it. It's 1.9. It can't be 1.9. E can't be greater than 1. It is, as Adam points out, scientific notation. That E represents scientific notation. Or in other words, we're going to move the decimal point 41 places to the left. Is this really big or really small? Really small. How small is it? Exactly. So typically, if you see like this sort of stuff reported in papers and so forth and analyses, they typically will round the p-value to the nearest 4 decimal places. So in this particular case, p would equal 0.0000, and no one is going to think it's actually 0. Everyone knows that there's always going to be some chance that what you're seeing is some random effect, right? Because nothing is perfectly precise. So they know that this is not literally 0. But what we do know is that it's super freaking small. Because if you get to 4 decimal points, you still get zeros. Right? That is, that reaches a very, very small alpha. That's still smaller than a very small alpha. That's statistically significant at any reasonable threshold you can imagine.
Any questions? So let me show you a quick and dirty way of this as well. Because quick and dirty is also pretty fun. And it has some nice illustrators in it, some illustrators. So what we can do as well is we can make a scatter plot with this data. Now, we want to set it up so that difficulty causes quality, which means we want difficulty on the x-axis and quality on the y-axis. Do you remember how to make sure that happens when working with scatter plots? Like if we were to make a scatter plot with this, we would just highlight both things, right? And it will default one as x and one as y. You remember which is defaulting where? Which goes where? Right. Exactly. So, because difficulty is supposed to be our x, but it's on the right, not on the left. How do we fix that?
For me, there's something on the point that said like axis. Change the axis.
Oh, I was just going to right-click E and size, and then right-click D and insert myself. And then that allows me to swap. And then I can highlight. Either way, I don't really know. I'm used to do it that way, so maybe I'm much better than just like moving your columns around. So, I'm going to go into insert and scatter plots. And there it is. I can manipulate this a little bit. Like, it's sort of annoying that there's a 6 here, because I mean it maxes out at 5. It can't be possibly higher than 5. Same story over here too. It goes out to 6. But this is the scatter plot, right? We can see that negative relationship. Each one of those points represents a professor. In fact, as a side note, it might represent more than one professor, because some professors might have the same combination of quality and difficulty ratings. So, okay, so it's overlapping them. Now, I would like to put in a line. I would like to put in a decimal line. And we call that as well the name for it is called a trend line. So, if you select the data, just put the data and right click it, you see this add trend line option. Press the add trend line. And it gives you this dotted line. It's like really irritating. We're going to stick with the linear, because that's what we're working with today. If you want to do crazy crap, you can as well. But linear seems appropriate here. Is everyone right here? Everyone have this one? No? Did you right click? Just right click on the data, the actual points. Then add trend line. There it is. Everyone else got the trend line? I'll go over here. Yeah. Why is it? Oh, okay. Why? I think I see what's going on. See, this is like hundreds and 200s. Did you highlight like number of observations and reviews? Already? Oh, so just to highlight that. Don't highlight the whole thing. Just highlight reviews. Yeah. And drag it to the right as well. But you want to make sure that difficulty is in the other column. So you want to swap your difficulty in and quality columns. Are we good? Yeah. One last question. Click the data. Go to the actual points. The right click. Enter. This is what. Oh, yeah, you can remove that if you want. Oh, I see. I see. So yeah, you have to swap them around. Yeah, because otherwise you're backwards. Yeah. You're right. So you're gonna have to make a new one too. So what I want to show you that once we've done that, if you scroll down, you see display equation on chart. Do me a favor and click that. And you get this. It comes out, and I'm going to drag it up here so you can see it. So once you have your trend line, right, if you scroll down on the right, there it is. Did everyone display equation on chart? That's because you need to swap your columns. Yep. Because you want to put your X variable on the top. Yes. Oh, I think I know how to do that next time. So you don't want to highlight the first row. Yeah, go over there. And then go to the right here. No. Here highlight one box. So don't make it highlight it. Highlight it as one box. So sometimes it'll work. Yeah. Okay. So, for those of you, as most people have this, all right, excellent. Note that when we display equation on chart, they put it in y equals mx plus b format, but it is identical to what we found right here. It's exactly the same thing. So in other words, it figures out the trend line by doing a simple linear regression, just like we done. Now, it's tempting sometimes to say, oh, I don't want to pull out data analysis then. I'm just going to use the scatter plot and then put a line of best fit and see what the equation is and then go home. And you can't do that, except when you do that, you don't get the p-values. You don't know if the variable is statistically significant or not. Like, this is a great thing to do for presentation purposes. You know, clean it up a bit, you see the trend line, that looks nice, but it's not great for analysis purposes. So keep that in mind, right? It's nice to have both skills and both tools at your disposal. Here's by the way a cleaned up version of that. Exact same thing. Yeah? No. I got rid of the circles. I like the boxes more. Circles are less distracting. I made it larger too, and I added nice, clean grid lines everywhere. Label my axes. It looks great, isn't it? Don't laugh. It does look great. So, but also too, what's neat about this is you can learn something about the individual professors because you can look at their residual. Take a look at this person right here. This person is pretty hard, right? They got a rating of 3.8 on the difficulty, which means they should be right about here at about 2.8, roughly 2.7, 2.8 on the quality. But they're not 2.8 on the quality. They're all the way up at like 4.2. If you look at a 4.2, you might think, oh, that person's pretty good. But given how hard they are, they're a lot better than what they quote-unquote should be. Just like we described, what are some of the other things that causes height besides age? What are some of the other things that cause quality besides difficulty? Why
would someone rate a professor higher besides the fact that they were easy? Why would someone rate a professor lower besides the fact that they were hard? Maybe they have class fun, right? So maybe they're enjoyable. Right? Maybe they have great personality. Maybe they are really well organized. Maybe they provide a lot of things for you to figure out how to help figure out material. Maybe they're just really good looking, right? Who knows? But a lot of those factors, personality, the ease of material available, how organized they are, these are things that really do matter for quality. These are the things that you might want to reward if you're an administrator, hypothetically. So you can say, well, look, this person looks like they're okay, but they're actually the best professor we have here because their residual is so large. Similarly, this person over here, they look like they're not great, they're kind of bad. But given how easy they are, they're like way below where they should be. I don't know who that person is, but they're way below the residual. So you can also look at this and mean, well, maybe that person isn't that great. Because the unexplained part, the things we can't explain, are really low. To caution you, this is not a perfect analysis. This is not a final analysis. For one, I'm assuming this relationship. It could be this relationship is true. The other thing is, like, this analysis itself has problems. Like, you see these poor folks who are at 5. Like, the highest you can rate is 5. These people could actually be 6s or 7s, but they can't actually go up beyond that. And that's not just true of these individual people. That's also true of what's going into it. Remember, these are averages of ratings. So for all I know, maybe this person actually is better because, there might have been like one person that says, oh, this person is great, they're a 5, but really that person, might have rated them a 500. And the average, this person is not great for most people, maybe they're great for some people. And that's not really captured. So there's a lot of limitations to this. There's also this issue too of like if you started making rules based on this and the residual, you might have some unintended consequences and so forth. So that's why I'm saying I'm not necessarily like sending this to administration and saying this is how we should be evaluated. And look at our professor and put in the difficulty, see what our quality is, and that people with high residuals are really great and people with bad residuals should be fired. Like that seems like a lot, especially since we're basing it off of great repetition data, which itself might be biased, right? As we talked about the self-selection issue. So it's one thing to judge someone, try to take their class around, but another thing to fire someone based on it. That's a bit tricky. That's a bit scarier. But it's still a really interesting tool. And it's really helpful to find unusual ones.
That said, as I mentioned, we could be wrong.
Maybe this is not the case. Maybe this is what's going on. Maybe this is the dominant effect. So that would mean that the D and the Q should be swapped, right? So if we wanted to claim the other way, would we have to rerun the regression? Or could we just solve for D? Should we do algebra or should we rerun the regression? What do you think?
It's not here.
It should just go.
Let's just do the algebra. So who said that? Yeah, it did, right? So I want to caution you against that. Because keep in mind what we did
To get this line.
we found the minimum vertical differences. Yeah, exactly. If you switch it, then you're technically at the horizontal differences. So there's no reason to think that this difference squared will be the same as this difference squared. So in fact, you have to rerun the regression.
And that's what I did here.
This is that same thing, but reversed. Now quality causes difficulty. And it's still statistically significant, but you see the equation is completely different. It is, we have 3, 5, 8. Fine, 01 minus, still negative, 0.6747 Q. It's completely different. If you could solve it, for example, you would solve it in the algebra, what's it called? The coefficient would be greater than 1 here. This is not only less than 1, this is less than what this was.
And to further illustrate that, take a look at them side by side.
When difficulty caused quality, this professor was exactly where we expect them to be. Right on the line. No mystery there. But when we rerun the regression, obviously we flip it on the XY line. Now this professor's over here, and they are no longer on the line. They are now unusual. They deviate away from that line a bit because there's a residual. So you can't go about it in line anymore.
So we have any questions?
That is one of the little possible homework. So that's more or less our very first introduction. You can see how powerful it is. I now know that if I make my class a little harder, maybe maybe my quality might fall by almost the whole point. If I improve my quality a little bit, maybe my difficulty will only fall by about half a point or 2/3 of a point, roughly speaking. That's pretty interesting. But as powerful as this tool is, its mathematical backbone rests on certain assumptions. And if you go in and do more advanced statistics, you learn more about how to test for these assumptions, how to correct the data if these assumptions are holding, how to maybe work around them, how to evaluate them, et cetera, et cetera. We're not going to do that, but we are at least going to understand what these assumptions are. And we're going to focus on 4 of them.
This sometimes I've seen analysis where there's more than 4.
We're just going to focus on 4. These are assumptions of linear regression. One. This one's really easy. This is the relationship is linear. Imagine the data looked like that. A scatter plot looked like this. If you were to try to force a simple ordinary least squared regression on it, you would get something that looks like that. That's not that great. Clearly, that doesn't really map well. This is not a linear relationship, this data is. There's a curve here. It's more of a logarithmic function. But because we don't
we had to incorporate that into our analysis.
We just get a straight line. And so
We have to assume the relationship is linear. There has to be some reason to think
that the slopes should be constant. Excel, by the way, has a little bit of this built in, so you notice that when you made that line of best fit, it said, oh, did you want to make this like an exponential function, or did you want to make this a polynomial or something like that? You can change it. It will automatically change it, but again, the problem is it won't tell you if it's statistically significant or not. So.
That's not right. 2.
The residuals follow a normal distribution.
In other words, most of the observations are going to be relatively close to the line of best fit.
A few are going to be really far away, but in general, it should follow a normal distribution just like we would see in the central limit there. Take all the residuals, plot them on a histogram, you should see something that at least resembles a normal distribution. This one isn't a huge deal for the kind of thing we're talking about, but it can come up in different kinds of analysis. The residuals should be independent from one another.
In other words, you can't predict one observation's residual by looking at the previous observation's residual.
They should be random.
This isn't really a big deal in cross-sectional data because, you know, if you think about our states, we've got Alabama, Alaska, Arizona, Arkansas, second alphabetical order, so it's hard to imagine one residual will predict the next residual when the order of the residuals are themselves randomized, right? They're based on alphabetical order here. But it does come up a lot in time series data, where there's a logical connection, 1975 and 1976, 1977.
Right? That's this logical thing, and so you sometimes see you can predict one residual by looking at the previous year, the previous quarter, the previous day's residual. Stock markets do this a lot. So when this happens, or when this doesn't hold, we call it autocorrelation. I feel like I'm going by pretty quickly. Does anyone have any questions so far? Yeah.
For number 3, when you say the residual should be you basically mean that like the dots have no connection whatsoever.
Yeah, you shouldn't see a pattern with the residuals. Yeah.
Like, I've seen this as just a hypothetical. Data looks like that, and you drew out a green line. So what you can do is so in this case, right, it's down, and then it goes up, and then it's down by the same amount, and then it's up by the same amount, and it's down by the same amount, and up by the same amount. That's a pretty bad autocorrelation. It's bouncing back and forth, right? Again, you're like, well, that looks like a pretty good line. It seems like a pretty good line, but it could have some problems and bias in the in how statistically significant, for example, the coefficient is.
In other words, maybe you're not really seeing random. Maybe you're seeing something else entirely. Nice, residuals and whatnot. The last one, we assume there is homoskedasticity. Say it with me. Homoskedasticity. Homoskedasticity. It takes a little bit of practice, but it's one of our assumptions. More interestingly, what is it? Let me illustrate with a scatter plot. That's really the best way to detect homoskedasticity. What do you think, by the way, is the opposite of homoskedasticity? Heteroskedasticity. Absolutely. Let's take a look at income, average income in a particular county, and percent of residents who own homes, who own their own home. Whether that home is a townhouse or a single family home or a condo, they are homeowners. Now, if a county has low income, do you think a large percentage of people are going to own their own homes? No. It's probably going to be maybe down here. Some, there may be some that do it. It's going to be mostly here. But as incomes rise, you think more people are going to own their own homes? Yes, but is it guaranteed? No, why not? What would be an example of a county that's probably pretty wealthy but still has low rates of home ownership? San Francisco. Why do you say San Francisco?
I was reading an article about people having a hard time purchasing homes because of extremely high rent prices.
Yeah, even though the income is high, the rent's really high too. In a large part because it's really hard to build, and there's a lot of it's really heavily populated, and so there's a huge scarcity. So they might have high incomes, and then for whatever reason, maybe there's low rates of home ownership, or maybe you have high incomes, but you live in an area where there's a lot of people who vacation there. So they're not really counted, so a lot of the homes are gobbled up and people don't live there, so that might have low rates. Or maybe they prioritize things besides home ownership. Or maybe I think given the income, I think this area probably has a pretty low level of home ownership because a lot of people move here temporarily and then leave to go do somewhere else because a lot of people hate this area. There's a friend of mine who recently moved away and is like, this is so exciting. No one talks about politics. This is so great. So he was happy to be away. So in which case, people are less likely to own their home because they know they're going to move away. And so when you look about this, right, if you plot this, it might look like this. There is this relationship, this positive relationship, but note how the dispersion bows out. If we were to draw a best fit line, they're tight around here, and then they get farther away. And this is heteroskedasticity. Homoskedasticity would be if the dispersion between the observation and the regression line is pretty constant. Not perfectly constant, of course, but at least relatively constant. Oops, I should have drawn it further right. Let's go over here. This is more homoskedasticity. This is heteroskedasticity. That's a sad county right there. For rich people, but no one owns a home. So, to put it another way, the variance on the regression line is the same. Or the dispersion. What's the dispersion?
Any questions on this?
Where's that say regression line?
Regression line, yeah. as a side note, if there is heteroscedasticity, it's not a huge deal. It tends to, as an example of like what happens, it creates this small bias
in your error, which makes it bias in your t-statistic.
Well, bias, you mentioned it's bias in your t-stat / p-value, because obviously the p-value comes from the t-stat. So, in other words, if you are right on the edge of statistical significance and you have heteroscedasticity, it might not be statistically significant. But if you get like p-values that are basically 0, and you would correct for this heteroscedasticity, it would still probably be statistically significant. It would still probably be 0, quite frankly. Like we had it with like 41, you know, e to the negative 41. Like that's really small. So even if there was some heteroscedasticity, right, corrected for, some of these assumptions are just sort of like on the edge, like you're on the edge and you have some heteroscedasticity, it's probably not statistically significant. Right? We have these clear lines in stats. But this is just an example. This is more of an aside as to the kind of complexity that comes into it and how you would unpack and evaluate. By the way, it's also a pretty easy thing to test as long as you only have 2 variables. Make a scatter plot. Make a line of best fit. 2 things bow out. They stay kind of in the same area. That's not exactly, that's not scientific. You're eyeballing it. But if you're ever curious, but it's not required. I wouldn't expect it in the memo.
Don't we have any questions?
I hate to, you know. I'm going to show you, I want to do one last thing too. There's no questions on this. I have literally 2 minutes, and I skipped over something in the notes because I wasn't sure I'd get to it. But just as a side,
You might be wondering why we square the residuals for line of best fit. Because one of the advantages of doing a line of squaring it is you get rid of the negative values, right? But watch this.
so there's good reason why we square the difference. And that is because if we didn't square the difference, then A, there would be more than one potential line of best fit, and 2, mathematically there'd be more than one line, but intuitively there would be a difference in these lines.
To give you an example, let me show you this hypothetical data set of 2 different regression lines here. Zoom in. Which one is a better fit? The blue line or the red line? The red line? Which one is a better fit? Yeah, no, the whole data set, we have 6 data points. Like, clearly the blue is the better line, right? So if you took the absolute value of the residual rather than the square root of the residual, though, they would be exactly the same. The red line, let's see what it does. It would be the red line, it would be 2 plus 2 plus 2 plus 0 plus 0 plus 0. And that's 6. If you do if you do this one, it will be 1 plus 1 plus 1 plus 1 plus 1, also 6. So they would be equally good. But if you do the squared method, this is 1 squared plus 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 1 squared. That's still 6. But this is 2 squared plus 2 squared plus 2 squared plus 0 squared plus 0 squared plus 0 squared. What is 2 squared plus 2 squared plus 2 squared? 12. So in other words, this would have a higher value. This is the lower one. So that's why we square. The absolute value method, there's no difference between these two. The squared method, the blue one is clearly better, and the blue one instinctively is better as well. Okay. So with that in mind, I will say goodbye to you and see you next time.